Deep within the periodic table lies an element unlike any other liquid at room temperature, silvery and strange. This is mercury, a metal that has fascinated scientists and alchemists for centuries. Today we're going to witness one of its most visually striking transformations. It begins with a chemical reaction, one that converts this liquid metal into a soluble compound. Mercury metal meets a powerful oxidizing acid, a reaction only ever performed by trained professionals in a fully equipped laboratory. The result is mercury nitrate, a colorless solution that holds the key to what comes next. But this step alone is where the real danger lies. Reactions between mercury and concentrated acids release toxic vapors, invisible, odorless in low concentrations, and hazardous to the nervous system. That's why this entire process demands specialized fume hoods, protective equipment, and expert supervision. With the mercury now dissolved, the stage is set for a striking transformation. A second solution enters the picture: potassium iodide, a simple salt with a powerful reaction waiting inside it. As the two solutions combine, something remarkable happens instantly. A brilliant orange-red precipitate begins to form, swirling through the liquid like a paint pigment. This is mercury the second iodide, a compound with a crystal structure that gives it its vivid color. The solid is separated from the liquid, isolating the pure compound. It's carefully dried, removing any trace of moisture. What remains is a fine, brilliant red-orange powder. This color isn't just a chemical curiosity, it's a signature of the compound's specific crystal lattice. At room temperature, mercury iodide arranges its atoms in a structure called the red or alpha phase. This phase absorbs light in a way that reflects red and orange wavelengths back to our eyes. But this structure isn't permanent, it's temperature sensitive. Now, we introduce heat. As the powder is warmed, energy floods into the crystal lattice. Atoms that were once locked in place begin to shift, and then, right before our eyes, the color begins to change. Red gives way to orange, then orange fades into a bright, vivid yellow. This is the beta phase of mercury iodide, a completely different crystal arrangement. The transition happens at approximately 127 degrees Celsius, a specific and repeatable threshold. In this new structure, the compound absorbs and reflects light differently, producing its yellow hue. Now, watch what happens as the heat is taken away. As the compound cools, the atoms settle back into their original positions. Slowly, patiently, the yellow retreats and red returns. This reversible color change is called thermochromism, a vivid reminder that beneath every color we see lies a story written in atoms and energy.